Okay, perfect. And hello everybody, and welcome to this One Word YoungStatS webinar. So this is an initiative organized by the YoungStatS project. Sorry.
Great.
Sorry. So are we good to go?
We are good. We are good.
Okay, perfect. Okay, so welcome everybody. So yeah, let me spend a few words before the proper start of the event. So this is an initiative by the YoungStatS project. This is a project basically aimed at promoting young researchers in all areas of probability and statistics and econometrics. And in particular, we are very grateful for the support from the Bernoulli Society, from the Institute of Mathematical Statistics, the IMS. And this organization of these webinars is part of this project. And in particular, I'm very happy that today we will have one focusing on stochastic fluid dynamics. So this is a topic which is very important for me, but also I would say it has become very unpopular in the last years, and it's both important from the theoretical perspective, like turbulence, but also in view of applications. And I think we will also see this with the 4 speakers we have today, who all come from different areas of Europe. But okay, without further ado, I will just leave the floor to our moderator of today, Umberto Pappalettera from the University of Pisa, who will manage this event. So Umberto, please.
Yeah. Thank you, Lucio. Just a remark, former from University of Pisa, now I'm in Bielefeld, but yeah, never mind. So 4 speakers, so I guess it will be a very dense session. I will introduce briefly the speakers. I propose, if there are questions to the speakers, if there are brief questions to the speakers,
Přesně ono. Takže oni prostě se na to podívají a pak jim to pošli.
And also please unmute yourself if you're not speaking. Okay, if there are brief questions to the speaker, you can just ask immediately. If your questions are more like comment and lead to further discussion, just we prefer to postpone everything at the end of all the talks. So the first speaker of today is Diego Alonso-Orán, who is currently a postdoc at the University de Laguna in Tenerife, and obtained his PhD in 2019 at the Universidad Autónoma de Madrid under the supervision of Professor Antonio Córdoba. Then we move to the second speaker of today, which is Daniel Goodair from Imperial College, with a PhD in the group of Dan Kriesen. The third speaker of today is Erwin Luesink, which was a researcher at University of Twente and got the PhD in 2021 from Imperial under the supervision of Derry Law. And the last speaker of today is Milo Viviani, who is currently a postdoc at Scuola Normale Superiore in Pisa, who got his PhD in 2020 at Chalmers University of Technology in Gothenburg, under the supervision of Professor Klaas Modin. So Diego, if you're ready, please share your presentation, and you can start whenever you want.
Okay, perfect. So just to check that everyone is reading everything properly.
Yeah.
Yes. Okay, perfect. Then let me just start. So first of all, thank you very much, Andrea, Lucio, and Umberto for the nice invitation and for putting all this effort together to run this webinar. So I will talk today about some regularity results for a stochastic transport equation with non-local velocity. But let me start from the very beginning. So fluid dynamics is a fundamental subject to improve the understanding of our world due to its endless applications in diverse areas. For instance, in ocean dynamics, in climate science, weather forecasting, medicine, and engineering, and so on. So the scientific community, and in particular, I would say pure and applied mathematicians, have tried to implement, design, and test different models to capture and to describe complex phenomena in the previous mentioned areas. So typically, these deterministic PDEs have been employed for this purpose. In particular, non-linear and non-local deterministic PDEs. However, there are certain limitations of these PDEs regarding small-scale phenomena or sensitivity dependence of the data. So somehow to compensate these limitations, there has been a new idea, which is modeling in a stochastic way. For instance, in weather forecasting, the inclusion of stochastic noise can be used to represent uncertainty and turbulence, two important phenomena. So somehow an ensemble of stochastic predictions instead of a single deterministic prediction. So from my point of view, PDEs, stochastic and deterministic, are somehow two different worlds. I came from the deterministic side and turned into the stochastic side in the last 2 years, but they somehow feed back and feed off each other. So things that can be done in the deterministic case can be somehow give some hints to know what you have to do in the stochastic case and the other way around. So instead, you can think that deterministic and stochastic worlds are completely different. There is some relations between each other. So since I came from the deterministic world, let me start presenting a wealth of transport equations that describe different phenomena in fluid dynamics. So these are called in general active scalar equations. And those are just basically transport equations where you have a quantity that we represent by theta, that is a transported scalar quantity. And then you have u, which is the fluid velocity, which is determined by theta through a certain operator t. So u and theta are related through a certain operator. So active scalars arise somehow from much more complicated equations as the full Navier-Stokes equation in different physical regimes as stratification, rapid rotation, porous media, geostrophic balance, so in different asymptotic regimes. In addition, it is important to notice that active scalar equations are nonlinear and the most interesting example also non-local. So probably the most familiar and well-known example of 2D incompressible system formulated as an active scalar equation is the 2D Euler invorticity, which probably everyone in the audience know. Here, omega represents the vorticity of the fluid, and the relation between the velocity of the fluid and the vorticity is given through this particular operator, which is called the Biot-Savart operator. So it is important to notice that the constitutive law between the scalar and between the velocity fluid is smoothing. So you are somehow winning one derivative. So it is known since the work of Wolibner in 1933 that existed a uniqueness of global smooth solutions for regular enough initial data for the 2D Euler equation. So you have global existence of smooth solutions. Perfect. There is also a very important model that is called the SQG equation, surface quasi-geostrophic equation, that is also a 2D active scalar equation. So SQG describes the dynamics of fronts as hot and cold air, and is used in atmospheric science, in particular to describe the phenomena of frontogenesis. So this was introduced in the book of Pedlowski, and it was, I would say, mathematically studied by a seminal paper of Konstantin Maida and Tabak in the 94. So theta, the scalar quantity here, represents the potential temperature of the fluid. And the important thing is that the relation between u and theta is not a smoothing. It's a zero-order singular operator. So there is no smoothing effect. Therefore, whether the SQG equation develops singularities in finite time from smooth initial data is in an intriguing and I would say a very hard open problem. To conclude, let me present a model that is now known as the CCF model. It was introduced by Córdoba and Fontelos, and it's a one-dimensional version of the SQG equation. So you have a transport equation in one dimension, and let's say that the relation between the u and the theta is, instead of the two-dimensional Riesz transform, right now it's just the Hilbert transform. So this equation is like a small brother of the SQG equation, and models the Bijorot equation describing the evolutions of vortex sheets with surface tension. So Antonio Córdoba, Diego Córdoba, and Marco Fontelos in 2005 proved that this model develops singularities in finite time when you start for a smooth, compactly supported initial data. So somehow this model is, for me, interesting because it's a little bit more complex than the classical Burger's equation, because let's say that the velocity is not now u, is a Hilbert transform of theta, so it's non-local, but it's still one-dimensional. So it's like both things, non-linear, non-local, but still one-dimensional. So it's difficult, but not so difficult, okay? So what we're interested today is to introduce stochasticity into these active scalar equations and study what is the difference of the solution's behavior from a theoretical point of view. So there are a lot of questions that we can think about. For instance, just to prove well-posedness of the stochastic PDE regarding existence, uniqueness, continuity from initial datum, and in particular, are there any crucial difference between the solutions or the behavior of the solutions from the stochastic PDE and its deterministic counterpart? There are also some interesting phenomena that are very, very hot topic right now, that is called regularization by noise, that, for instance, does the noise restore uniqueness? Can the noise expand the lifespan of the solution, or even prevent the formation of singularities in finite time? And the last question is, for instance, can noise improve the continuity with respect to the initial data? So those are the questions of interest. And of course, I cannot give you an answer of the three of them, because it depends on the particular structure of the PDE that you are analyzing. And moreover, also, it depends on the particular type of noise that you are using. So in today's talk, I will just center in the CCF model. So we will try to understand what is the behavior of the solutions of the CCF model, the Córdoba-Fontelos model, when we put random perturbations, okay? So here we have the equations. W is just a cylindrical linear process, and H will be, in general, a nonlinear function. So this is a joint work. Everything that I will tell from now on is a joint work with Hao Tan from the University of Oslo and Jingting Miao for South China University of Technology. Okay, so let us continue. Let us start with some very basic definitions and some assumptions on the noise. So just a spoiler, I will not talk about transport noise. Everything will be just about multiplicative noise, okay? So probably the next talks will just focus on this very nice transport noise, but not in this talk. So, okay, so we have the triplet omega, F, and P, which denotes a complete probability space, where P is the probability of the measure on omega, and F is the sigma algebra. So let us define what are pathway solutions. What are the definition of solutions that we will work with? So fix an S, the stochastic basis, give me S bigger than 3/2. Then we say that a local pathway solution to our problem is a pair U and tau, where tau is the stopping time, which satisfies the typical properties that it is continuous with respect to time, HS in space, almost surely, and it also satisfies the equations in this integral sense, okay? The local pathway solutions, you say that they are unique when you have two of them, which start with the same initial data and then coincide for the latter times, okay, with probability 1. It's basically saying it in a rough way. And then we also have what is called the maximal pathway solution, which is this U, which is the pair U tau star, which basically saying that you have the, this is called a maximal pathway solution to P if tau star is bigger than 0 almost surely, and if there exists an increasing sequence such that this condition is satisfied. Okay, this is probably known by everyone. It's just a definition of the solutions that we will consider today. So let us remember what was our equation. It's just the Córdoba-Fontelos equation with this right-hand side that is some multiplicative noise, okay? So what is the first assumption that we will put into our noise HTU? So we will assume that when h is bigger than 3/2, this h is continuous from u to hs. This L2 u hs is just the Hilbert-Smith operator. And furthermore, we will also assume the two typical conditions for the noise. The first one is just the growth condition. So the noise can only grow in this way. And the second one is the typical Lifshitz condition for the noise. So these more or less typical conditions to ensure, let's say, existence, uniqueness, and maximal pathway solutions. So a particular example of this noise, if you want to think about something precise, is just take W, just this calligraphical W equal to W, which is just a one-dimensional Brownian motion, and just take H of TU, this noise here, okay? It just depends on time in this way. Let's assume that Q is a smooth function, which is upper and lower bounded. And this is just an operator that takes into account, let's say, nonlinear terms of UX and nonlinear terms of HUX. Okay, so you do a little bit of computations and you can check that this noise in particular satisfies both assumptions. Perfect. So with these assumptions in mind, what we can show, again, joint work with Hao Tan and Jinting Miao, is that for S bigger than 3, and HTU satisfying the previous assumption, we can show that there exists a local unique pathway solutions to our problem, L2 in probability, continuous in time, and HS in space. Moreover, U tau can be extended to a unique maximal pathway solution with the following blow-up criterion, which relates the norm of HS of the solution with the norm of UX in L infinity and HUX in L infinity. So basically, this is saying that if these things blows up, these things blows up, and the other way around. Okay, so this is what is known as a blow-up criterion. Perfect. So let us just mention some points of the proof. So for U smooth, when you do the a priori L2 HS estimates for you, you use ETOP formula, and then you get basically two terms. The first term is coming from the noise, and the second term coming from the nonlinearity. And you want to bound it by this right-hand side. Of course, since you cannot split the mathematical expectation, what you usually do is to put a cutoff into the nonlinear parts, a cutoff in the nonlinear parts in terms of some norm in HR, with R is a suitable norm which interpolates between HS and W1 infinity. You prove the a priori estimates, and this is basically, let's say, the way to proving the a priori estimates with the cutoff in the nonlinear terms. Of course, this only works for S bigger than 3 and R equal to S minus 3/2 in order to this embedding to work. So what is the problem here? The problem is that when you want to pass into the limit, so you can prove uniform estimates, but you want to pass into the limit, usually in bounded domains, you have this classical embedding where the first embedding here, it's compact. And this combined with the uniform estimate, as you have already proven, it's sufficient to obtain convergence via Prokhorov theorem and Skorokhov theorems in HQ. However, in our case, this is not as easy as we are working in an unbounded domain. So the things that you can do is you have to prove something else. Let's say that this embedding in R is true when you put here log. So it's only true in the log space. And even though you can prove the uniform estimates, this is not sufficient to pass to the limit. So what you have to do is to establish convergence results of functions in a topology that is not weaker than HR. Okay, so this basically the novelty or somehow the difficulty when you compare into the bounded domains, for instance, in the torus or things like this. So you have to really work a little bit to approximate solutions that are converging in this higher order. Okay. So this is just things about the first result. The second result is a little bit much easier in the sense that we just put linear noise. So this is called weak linear noise. And what we proved is, okay, this linear noise is just a function of time that is continuous and that is upper bounded. So the theorem that we prove is the following. For this equation, with this linear type of noise, assume that you have an initial data, which expectation is finite, and that it attains a global maximum at some point. Moreover, if this lambda u0 is bigger than some quantity that has to do with the noise, where B star is the one that we, in assumption B, then what we can prove is that the unique maximal pathway solution blows up. Okay, so there is finite time blows up. I will explain right now what is this lambda u that is quite important. Okay, perfect. So let me make some observations and let me give a very, very brief sketch of the proof. So the point is that since you have a linear noise, you can use Gibson-of type transform to obtain a PD with random coefficients instead of a SPD. So the lambda here denotes just the derivative of this Hilbert transform. So the derivative of the Hilbert transform is lambda u. And this lambda is basically the fractional Laplace operator. So it's easy to show that basically when you work with a linear noise, this is a particular noise, and it also satisfies assumption A. So you can provide the same blow-up criterion. And what we just did is change HUX by lambda u, okay? And the thing that we want to prove is that the limit sup, when t approaches the maximal tau, of the maximum in x of this lambda u blows up. This is the thing that we want to show. There is a key identity that is used in our analysis, which relies on a pointwise identity proved by Luis Silvestre and Vlad Bicol to show that C1 solutions cannot exist for a deterministic CCF equation. In particular, when you put B star equal to 0, so when you recover basically the deterministic, we recover basically the deterministic result. Okay, there is a small thing that I have to comment. That is basically that due to the presence of noise, this condition in the stochastic case, in our case, it's a little bit more restrictive than the one in the deterministic case. In the deterministic case, if you just select one u0, where the lambda u0 is just bigger than 0, this suffices to prove the finite time blow-up. So it's somehow in the stochastic case, it's a little bit more restrictive. You have to be not only positive, but bigger than some quantity that depends on the noise. Okay, so how does the proof work? Okay, I will be very quick here. So using the typical Gibson-of type transform, you can go from our original SPDE to this random TDE. Okay, perfect. And once you're here, what you say is the following. Okay, let's select some x0 where u0 attains the global maximum. Okay, in the global maximum, we will denote it just by B, which depends, of course, on the probability, times 0, x0, and this is just the maximum of u0. Okay, let's hear that B and U are related via this transformation. Okay, so now you can talk about a particle trajectory mapping related to the process B, which is just given by this standard ODE mapping, so to say. And you can prove that this thing has a unique solution. Okay, then what you want to do is to try to compute the evolution of this operator lambda B in the maximum, okay? And you do computations, you derivate here in time, you use the chain rule, you use the equation, and you arrive into something that has this form here, that relates the derivative of this quantity that you want to see that blows up with this terrible right-hand side. Okay, redoing some kind of change of variables, you define this B tilde, you check that if B tilde is defined that way, the Vx is now lambda B tilde, and lambda Vx is now minus B tilde xx. You denote C0 just by to shortcut the notation, and let's omit the dependence of omega and t. What you get is basically this equation here. Okay, and here's where it comes the magic. And the magic is that you can show that for almost everywhere omega and t from 0 to t star, the following pointwise identity. And this is basically the beautiful idea that Vlad Bicol and Luis Silvestre had in order to get an expression, a beautiful expression of this part like this. And why is this interesting? This is interesting because if you just plug exactly the quality that I have just shown, you get this equation here. And this part is, of course, positive, so you can just drop it. Just calling f omega t this lambda b, what you get is the following inequality here. And now it's very easy because this is the typical ODE that blows up if you select basically the initial data in a sufficient intelligent way. Okay, and this can be done. You can do some computations, and this can be done, and you prove that for linear noise you get a blow up. Okay, finite time blow up. Perfect. I don't have too much time. I'm already 1 minute away, but just to comment one thing, we can also show for the same equation, now you have another noise. The assumption C of the noise, I cannot put it because it's very technical and somehow a little bit strong to write here down. But there are some assumptions. For instance, a particular case of this noise is this following one, okay? Which tells you that if you look this equation with this assumption on the noise, then what you can prove is that the corresponding maximal pathway solution to this problem satisfies that the probability of tau star equals infinity. So basically, what you can show is that you can kill or you can prevent somehow the blow up by taking these strong noises, okay? So it is true that this noise is somehow a little bit artificial and it's a little bit ad hoc in order to kill the growth of the nonlinearity, okay? This is why you can prove basically global existence for this equation. So just to conclude, we have studied the behavior of solutions to the CCF model and the different type of noises. So assumption A of the noise provides you of local existence, uniqueness of maximal solutions and blow up. Assumption B provides you of finite time singularities, and assumption C proves the prevention of these finite time singularities. Just one last comment. A future open dream problem for me would be the following. Let us add some dissipation into the system, dissipation where alpha is in this range, and try to prove that this equation blows up in finite time. So this is not even known in the deterministic case. So it would be a very, very interesting problem whether you can cook up here some kind of noise and show that this equation blows up in finite time. So I conclude here. Thank you very much for your attention.
Thank you very much, Diego. Are there quick questions? Yeah, you have a question in the chat.
Okay, let me try to see the chat. No. Okay, let me check. Okay, I will answer the question of Joris, if that's the question. It's the only question that I will. Is S also present in the deterministic result about the blow-up? No, this is not present in the deterministic result. In the deterministic result, you can prove basically existent just by taking S bigger to than 3/2. The typical embedding of the typical embedding of W1 infinity, let's say HS into W1 infinity. So S bigger than 3/2 suffice. However, in the stochastic case, you have to put this cutoff in the nonlinear terms, and in order to prove the convergence in the deterministic case, you don't need these cutoffs in the nonlinear terms. But in the stochastic case, you need to put these cutoffs in the nonlinear terms, and you have to pay by improving or by putting an S that it's bigger than 3/2. Okay, so whether this is sharp, I don't know. Maybe you can prove something better. But let's say that to use the classical techniques to prove compactness and passing to the limit, we only can show it for S equal bigger than 3. I think that's the question that I read.
Thank you, Diego.
You're welcome.
Yeah. So next speaker is Daniel Goodair. Daniel, can you please share your screen?
Yes. Looking good?
Yeah, perfect. Please go ahead.
Cheers. So firstly, thank you very much for the invitation. It's a pleasure to be here. So I'm going to be talking about the introduction of boundaries into stochastic fluid dynamics equations with a transport type noise. So if you are in this area of transport noise fluid dynamics equations, you've probably seen that pretty much all of the analysis happens in the absence of boundaries. So I'll just be discussing kind of the fundamental problems that you hit with a boundary, what we can and cannot cope with in our usual methods. There we are. So the model that we're going to use to drive this discussion will be the Salt-Navier-Stokes equation. So SALT here stands for stochastic advection by Lie transport. This is the methodology introduced by Darrell Home in 2015. And the equation is just given here in velocity form. So this is the classical Navier-Stokes equation. This calligraphic L here represents a nonlinear term. We're in capital N dimensions, which will be either 2 or 3. But now we have this Stratonovich integral, which has a representation as an infinite sum of components of BI, our salt operator, against standard independent one-dimensional Brownian motions, where each BI is an L xi. So this is the usual transport term, a xi dot grad. Xi here represents physically spatial correlations. We'll always assume that they are divergence-free and 0 at the boundary. We have to assume that they are sufficiently small for this infinite sum to make sense. However, we're certainly not assuming that they are small relative to the viscosity. Then in addition to that term in this SALT methodology, we have the 0 order operator T. So you can see in this T, the gradient is hitting what would be the xi. So this is a 0th order term. So this is the characteristic of the SALT operator. And in practice, we'll work with an equivalent form of this equation. And I say equivalent lightly because there really is some nuance between identifying these two equations. But essentially what we've done from here to here is we've taken the Lie ray projector of this equation. So this is the operator P that you see appearing. This is the projection in L2 into the space of divergence-free functions, which satisfy that the normal component at the boundary is 0. We've also incorporated the P into this operator A, which is the Stokes operator. This is just minus Lie ray projector of the Laplacian. And then what we've also done is we've converted the Stratonovich integral into an Ito integral plus an Ito-Stratonovich corrector. And so just to highlight at least a slight difference of the SALT methodology instead of just a purely transport term. So if you'd be looking at this, you'd say, well, we take the Lie ray projector and then we convert it. We'd actually be looking at this corrector term being PBI all squared. But actually, because of this additional T, this means that each BI preserves gradient. So if you take the BI of a gradient of a function, you get back a gradient. And so what this means is that PBI is actually equal to PBIP. So this is the same thing anyway. And you can also choose to look at this as, well, I want to convert from Stratonovich to Ito and then project it. Then because the pressure term you have here is a semi-martingale, then you do get a contribution in the Ito-Stratonovich corrector from this pressure term. But again, because the BI preserves gradients, that contribution just gives you a gradient again, and then the Lie ray projector will kill it. So ultimately, you do end up with this equation either way. So we want to add boundary conditions. So you can say, well, we're talking about Navier-Stokes. There's a classical boundary condition. This is that the velocity is 0 on the boundary. And this is called the no-slip boundary condition. And if we want to set up analysis for this, we need a basis, and we have a basis. So we have a basis of functions AK, which belong to the space W12 sigma. So this is a space of functions in W12, which are divergence-free and are 0 on the boundary. So this is really where we want our solutions to be landing in. They are eigenfunctions of the Stokes operator A, form an orthonormal basis in L2 sigma. So this is the corresponding L2 space, so divergence-free and weakly the normal component is 0 at the boundary. And then they also form an orthogonal basis in this W12 sigma space. And to use our analysis, we'll also define finite dimensional projection operators onto the span of the first n of these basis vectors here. So what is our solution method? So we're talking about how can we get existence of solutions just first of all. We kind of have a general solution method for all of these types of equations. So firstly, we'll consider a Galerkin scheme. So this is, we take finite dimensional approximations of the equation. So in this case, we just hit the equation by Pn and solve this. This is quite straightforward, but I would say it's not entirely classical because we still have an infinite dimensional driving Brownian motion. I couldn't actually find anything in the literature that said if you're in a finite dimensional Hilbert space and an infinite dimensional driving Brownian motion, then the usual conditions of Lipschitz and linear growth constraints give you well-posedness. But I have actually shown this in my notes, and it's not problematic. Just mentioning that I wasn't previously aware of this result, but there is no issues there. Then what we do is we'll look at these finite dimensional approximations, and we show that they are uniformly bounded in the energy norm of the relevant solutions. So for Navier-Stokes, if we're talking about analytically weak solutions, that energy norm is L infinity in time into L2 in space, and L2 in time into W12 in space. For strong solutions, this is now L infinity in time into W12 in space, L2 in time into W22 in space. Then some clever stuff is going to happen. And this is where we deduce the existence of a limiting process which satisfies the required identity. And so there's really two main mechanisms we have to do this. One of these is through showing a Cauchy property for this approximating sequence, and another is through tightness and relative compactness type arguments. So the purpose of this talk is not going to be going into the details of this, is really just looking at the fundamentals of introducing the boundary into these equations. So in fact, we'll be discussing the previous point in just showing the energy estimates in the presence of the boundary. And so with this said, then we have a limiting process. This then inherits the regularity from the uniform boundedness, which then gives us a solution. Okay, so let's have a look at these energy estimates. Let's start with analytically weak solutions. So what is the noise contribution in the energy estimates for analytically weak solutions? Well, the energy norm is now arising from an L2 in a product. So we're taking an L2 in a product here and an L2 norm. UN here is representative of the nth order solution. And in our energy estimates, this will be popping up as an integral in time, which is isolating what we need to consider here. This term on the left-hand side is what appears from the Ito-Tritonovich corrector in our energy estimates. And the term on the right comes from the quadratic variation in applying the Ito formula. So can we control something like this? Well, yes, actually, this is fine. So we can use the fact that Pn and the P are orthogonal projections in L2. So we can take the projections over. In this norm term, we can use that the norm of the projections can be bounded by the unprojected function. So we can get rid of those projections. And then what we have here in this line, well, we can take one of the BIs over to the other side. This is through using the adjoint. And we know that just for the transport operator, the adjoint of that is its negative, which will give us some cancellation. It's the same principle behind getting the cancellation in the nonlinear term. And if this was just a purely transport noise, that would be the end of the story, and this would just be zero. We need to work a little bit more here because of the presence of the zero order term. It then means we're retaining a first order operator on the left-hand side of this inner product. But we can use commutator estimates. It's not too big a deal. And ultimately, we can control this for analytically weak solutions. And then we can go on and prove the existence of such solutions. But if we look at analytically strong solutions, then things become a bit more difficult. So for the energy norm in this case, this arises now from a W12 in a product. So this is the subscript 1 you can see here is the W12 in a product and norm. Now, if you want to handle this, well, we have that each Pn is an orthogonal projection on W12 sigma. So this again is space of functions divergence free, but 0 on the boundary. But then the Pn is acting on the Lie projection of something. And P does not map into this space. So we have, even for compactly supported functions, you hit them by the Lie projector, they may no longer be of 0 trace. And so what we have is that whilst the action of P gives you a function which has a representation in terms of this basis, is only in L2. And we don't know that this is a representation in W12. And in fact, as our basis is of 0 trace functions, we know we're not going to be able to approximate all functions in the range of the Lie projector, because the W12 limit of 0 trace functions is again 0 trace. So this ultimately means that whilst Pn is self-adjoint in W12, restricted to W12 sigma, we are not restricted to W12 sigma here. And so we can't just play the same game of getting rid of the Pn like we did. So what we can do, if we look at the norm term, so we can actually bound this by something without the Pn, but it comes at the cost of a constant C, which is going to be greater than 1. And if you saw in the previous slide, we relied on very precise cancellation of the derivatives in order to get sufficient control in our energy estimates. And so with this C being greater than 1, we no longer have the correct cancellation coming from the other term. And we just have another derivative that we can't control. And so we can't get past this just in this kind of classical method anyway. And still, to my knowledge, this is something that hasn't been done, showing that analytically strong solutions of the Navier-Stokes equation with a no-slip boundary condition exist, 2D global, 3D local, anything matching the deterministic theory. But is this the end of the story? Well, this is the most classical choice of boundary condition, but it's not the only choice. And so now I propose we consider the Navier boundary conditions as well. So in order to define these, let's introduce the rate of strain tensor D. So this is a matrix-valued differential operator, as you see on the screen, mapping F to this matrix. Then the Navier boundary conditions are that the normal component of the velocity at the boundary is 0. So this is just saying that our fluid cannot penetrate the wall of the boundary. We know we're going to need this. And then it also satisfies this condition in terms of the tangent. So this iota is the unit tangent vector. The D is the same one that we've just introduced. And then there's also this function of the boundary alpha, where alpha represents a friction coefficient. So now instead of the fluid velocity being 0 at the boundary, it's allowed to slip along the boundary, and the extent to which it slips is determined by this alpha. And these are not conditions that I've made up to just solve a problem that we faced. These were first proposed by Navier. They have since been derived from the kinetic theory of gases and as a hydrodynamic limit, so coming from physical principles there. And these conditions have also proven viable for modeling rough boundaries. So there's certainly a use for these boundary conditions in the literature. But from the analytical perspective, if you're anything like me, you look at these boundary conditions and just think, that's not something I want to be working with. That does not look very pleasant at all. But luckily, some very clever people have established properties related to the boundary conditions which make these workable and make them a lot less scary. So let's have a little look at what we're dealing with now. We need to introduce the relevant function spaces. So let's define W bar 12 sigma. So there's now a bar over this space as the intersection of W12 and L2 sigma. So this space now is characterized by functions in W12, which are divergence-free and just have the normal component 0 to the boundary. So we're not prescribing anything on the tangential component here. And then in this W bar 22 alpha space, this is now functions in W22, which are divergence-free, have the normal component equal to 0 on the boundary, and satisfy this property in terms of their tangential component. And so ultimately, this is a space of functions which are divergence-free and satisfy the Navier boundary conditions. So this is now where we'd be looking at our solutions to land. And so what properties do we have relative to this space? Well, when we're talking about Navier-Stokes on a bounded domain, we certainly need to be sure that we can handle the Laplacian that pops up. We need to be able to do an integration by parts type argument to turn this Laplacian into a positive term for us with a gradient on either side of the inner product. And so in the usual no-slip case, this is just very straightforward. You just do the integration by parts and there's no boundary contribution. With Navier boundary conditions, what we can say is, well, we can do this integration by parts. So taking the Laplacian over into a W12 inner product. So this is then the end of the story for the no-slip case or on the torus. But now we do have a boundary integral coming into play here. This is L2 over the boundary. Kappa here is the curvature of the boundary, and alpha is the same alpha popping up in the boundary conditions. But if we didn't have any boundary information, just using the Green's type identities, we would have a derivative here. And then this would be too much for us to handle in our energy estimates. But the Navier boundary conditions give us enough information that there is, we don't need a derivative in here. And then this is a boundary integral, which we will be able to control with trace estimates. So this is one property coming from the Navier boundary conditions. In addition, if we introduce the curl in 2 dimensions, so this is now gives us the usual scalar valued function, and one line too late, let's define kappa as the curvature of the boundary. Then we do also have that the Navier boundary conditions satisfy a relation in terms of the curl. So for all functions f in W22, if the normal component is 0 on the boundary, then we have that any such function satisfies this relation. And so the keen-eyed among you will see the similarity between what we have here and what we have in the Navier boundary conditions. So we're not assuming any tangential properties of f at the boundary. So this is all functions satisfy this property. And so in particular, we can take a corollary from this lemma, is that for any function f in W22, which is tangential at the boundary, then f satisfies the Navier boundary conditions if and only if its curl satisfies this property. So actually, you can see the Navier boundary conditions as conditions on the vorticity. And a very interesting particular case is then, well, if we prescribe that alpha is equal to 2 kappa, then we're prescribing that the vorticity is just 0 on the boundary. So this perhaps gives us some information now to be slightly less scared of the Navier boundary conditions. We know they have a characterization in terms of their curl. So let's set up our analysis again in this setting. We again need a basis, and we do have a basis. So this is now a basis of functions a bar k, which belong to our space of functions which are divergence-free, satisfying the Navier boundary conditions. They are eigenfunctions of the Stokes operator, an orthonormal basis in L2 sigma, and now they are an orthogonal basis in this W bar 1, 2 sigma. So you see our tangential requirement on the boundary condition now involves a derivative. So we're looking at the trace of the derivative, which then we need more than W12 information for this property. So whilst previously in the no-slip case, we had that any function satisfying the boundary condition, well, there's 0 trace, any W12 limit has to again be 0 trace. Now we have that we can actually take functions which satisfy the Navier boundary conditions, and their limit in W12 doesn't necessarily have to satisfy the boundary conditions. This spans in W12 a wider class, and in particular, it spans the range of the Lie ray projector in W12, which was an issue that we faced before. So let's also define now P bar n as the orthogonal projection onto the span of the first n of these basis vectors like we did before. Then if we just look at the same term which was so problematic for us in the no-slip case, again, this is a W12 inner product, but now with these new boundary conditions. Now, because of this new property that we have a basis in W bar 1, 2 sigma, well, the projections are self-adjoint on this space, and this is the range of the Lie ray projector on W12. So what we can do is we can get rid of these finite dimensional projections, as in we can create an inequality with this on the right-hand side, which is something that we couldn't do in the previous case. And now there is a lot more to the story here. We still have a Lie ray projector. It doesn't make everything entirely trivial now. There are some really quite nice ideas that have to be invoked to control what is remaining in terms of commutator estimates and boundary integrals and things, but we can deal with those. And so just at the kind of zoomed out level of this talk, I'm just making the point that in the no-slip case, we did have a definitive issue which we can address in the Navier boundary condition case. And then we can go on further and control this integral for ways that I don't have time to discuss in this talk. So just to conclude then with what our results, conclusions, and future directions are related to this work. So for technical reasons, we are going to require that alpha in the Navier boundary conditions is greater or equal to the curvature. But in this case, we can prove the existence of a unique global strong solution to the Salt-Navier-Stokes equation with Navier boundary conditions. What's more than that is actually if we work on a convex domain so that the capture is greater or equal to 0, then we do have the existence of a martingale weak solution of the Salt-Euler equation obtained as an inviscid limit of the above solutions in the specific case alpha is equal to 2 kappa. So if you recall, this case at alpha equals 2 kappa is where we had the vorticity as 0 on the boundary. So this allows us to very directly show nice energy estimates on the vorticity. And in fact, we can use this to take an inviscid limit of these equations and show that weak solutions of the Euler equation exist, which is something that seems very, very difficult on the bounded domain. Other kind of inferences we made, well, it appears that the Navier boundary conditions are more compatible with the transport type noise than the no slip condition. It also appears that salt noise is more compatible with the boundary than purely transport noise. This is coming from the interaction that we have with the Lie projector and the salt operator. We don't have the same nice interaction if we just have a transport term. And then finally, just for some directions looking forwards, so Lucio introduced this idea of the scaling limit, which has led to enhanced dissipation ideas. So this is saying that for a very well-chosen Stratonovich transport noise, you can get a Laplacian as your Ito-Stratonovich corrector, and then an Ito integral, which can be chosen to be arbitrarily small in some sufficiently weak sense. And so what you have then is that your Stratonovich equation is very close to a deterministic equation with added Laplacian in it. And so this has already been used to show that for any initial condition and any given epsilon bigger than 0, you can find a noise such that the corresponding 3D stochastic Navier-Stokes equation has a global solution with probability greater than 1 minus epsilon. This was shown by Flandoli and Luo. And so this is the enhanced dissipation mechanism. And so what I'm interested in now is, can we establish the inviscid limit in the no-slip case with high probability? So this is a very famous open problem. So I said the inviscid limit holds for the Navier boundary conditions, which is a theoretical bonus for these conditions. But for the no-slip case, this is very difficult, and it's completely unknown deterministically. But if we can use this scaling limit idea, this mechanism for enhanced dissipation on the bounded domain, then we would be able to have success with this. So the question is, does this scaling limit idea pass over to the bounded domain? And that is a very difficult problem. The bounded domain with the Dirichlet zero boundary conditions. So if anybody does have ideas on this, how this idea might carry over, I think it would work to prove a really nice enhanced dissipation result. I've currently got very little, but if anyone is interested in something, please do let me know. I'll be very open to collaboration. But anyway, that is it from me. So thank you very much. Cheers.
Thank you, Daniel. You have a question in the chat by Andrei. So how related is the usage of Navier conditions to the usage of type of noise? Would your analysis significantly change conditional on the noise used?
Yeah, so if we look at well, the term that we need to control, so here, if the noise didn't have any gradient dependency, for example, then we could just well, let's actually go back to this one. Here we are. So if the noise didn't have any gradient dependency, then as we've seen here, we've just bounded this by a constant. And then with the Lie projector, you could bound this by another constant. And then if this BI was satisfied some boundedness in the same space, then you could just bound this again by another constant. And so there isn't really any nuance required in cancellation. And so you can just really just brute force bound. And then you get a bound which is in terms of the W12 norm of UN. And so then this is completely fine. The only issue then with the Navier boundary conditions, well, so the issue is why we needed to look at the Navier boundary conditions is for a transport type noise, we can't do that. We have an extra derivative that we need to be very, very careful in cancelling. And so the Navier boundary conditions allow us to do that. But the framework of, considering the Navier boundary conditions, this all comes from deterministic literature. But we just had to look to that to find a way to cancel these derivatives, which we wouldn't have to do if this wasn't a transport type noise. And, there are results. I mean, there's Nathan Glatt-Holtz has a couple of papers on both Euler and Navier-Stokes for a general noise which is bounded in the same norm on bounded domains. There's no issues with that. It's only with the transport noise that we have to be a lot more precise.
Any other question for Daniel? Okay. If not, we move to our third speaker. Thank you, Daniel, again. We move to our third speaker, Erwin Luesink.
Yeah. Let's see. Share.
Yeah.
Looking good?
Perfect.
No.
Go back in the full presentation mode.
Yeah. Sorry. Yes. Okay.
Perfect. Yeah.
Well, thanks, Umberto, Lucio, and Andre for setting up this very nice meeting. I want to talk a little bit more about the geometric story behind stochastic fluid dynamics, because these equations, they come from physical principles, and these physical principles are tightly interconnected with geometric notions. So when we introduce noise into fluid dynamics, we'd like to have these physical principles intact under the introduction of the noise. And this means that we have to think of noise in a particular way, and this leads to transport noise, as we will see in a moment. Okay, so this talk talks a lot about things that require quite a few people altogether. So one of the important collaborators is Paolo Cifani, who built the main code that we use to run some of the simulations. And then together with Sagi Efrati, Arnold Franke, and Bernard in Twente, we've developed further these numerical integrators, and we can also view a bit more of the geophysical fluid dynamics problems. And then with Daryl comes the whole notion of stochasticity in geometric mechanics. So it's the results I'll be showing for the geometric machine that introduced the noise is really coming from Daryl's 2015 paper. And then with Klaas and Milo, we built further this real a numerical infrastructure that lies underneath with a very particular kind of discretization that turns out to be exceptionally good on the sphere. And this is also why we will talk about the sphere a little bit further. And you have to acknowledge some funding, because this talk uses some numerics, and this numerics requires some computational infrastructure that requires a little bit more than a laptop for some of the simulations. So we used the Dutch supercomputer for this, and this I wish to acknowledge real quick. Right. So let me move on. So for this particular talk, we're interested in one particular example, and that is the recent work of Franco, Lucio, and Dejin Luo. They show that there's a scaling limit of stochastic 2D Euler towards deterministic Navier-Stokes on the flat torus. And we wish to investigate a related problem, numerically with structure-preserving integrators. So we're not going to delve too much in the rigorous analysis of this problem. We're going to focus more on the numerical integration of this problem. We have a very good numerical discretization for 2D deterministic incompressible fluids on the sphere. Now, the sphere is a natural domain for geophysical fluid dynamics. So we're going to try out this idea of the scaling limit of stochastic 2D Euler, but on the sphere rather than the flat torus. And then the question is, how do we extend this problem to the stochastic setting, and how do we observe similar results? That is the main question of this talk. And so these are the simulations you see below. This is the deterministic case. On the left, you see Navier-Stokes on a sphere that's not rotating. Then in the middle, you see Navier-Stokes on a rotating sphere. And on the right, you see a quasi-geostrophic model with some dissipation also on a rotating sphere. And these require quite a bit of intensive computing, but they do deliver very nice pictures. Right. So our goal now is to introduce noise into fluid dynamics in a systematic way so that many of these deterministic invariants that come from this geometric approach are preserved. Now, we want to attack the problem of stochastic 2D Euler. Oh, oops, some sound. Okay, we want to tackle this problem of stochastic 2D Euler, but on the sphere. And so we need to introduce noise into fluid dynamics in a geometric way to have equations that stay on the sphere. Also these numerical algorithms, we like to be robust and affordable, but that's something I won't focus too much on this particular talk. So the central geometric tool that we need to use to derive equations in fluid dynamics on smooth manifolds in general is the so-called Euler-Poincare theorem, and we want a stochastic version of this thing. Then this stochasticity can be introduced in several ways via something that we've now called the transfer principle to obtain a stochastic Euler-Poincare theorem. The main transfer principle, I think, dates back to Malianvin, who introduced the first such notion. We then use this stochastic Euler-Poincare theorem to derive the 2D incompressible Euler equations on the rotating sphere, and then we quickly discuss which invariants we're talking about. And then we want to numerically investigate the convergence of stochastic Euler towards deterministic Navier-Stokes for small-scale noise on the sphere. Okay, so first get started with the stochastic Euler-Poincare theorem. So geometric mechanics uses the notion of a Lagrangian or a Hamiltonian, and then a variational principle or a Poisson bracket to derive the equations of motion. So in this picture on the back, you see the Lagrangian, which is a functional on the space of tangents to the diffeomorphism group. And the diffeomorphism group is the space of smooth maps with smooth inverses, where we have a little extra notion. There's a little S there that says that we discuss Sobolev class diffeomorphism with a certain smoothness. And this is to avoid a number of topological issues that you get into if you take smooth diffeomorphisms in general. Then on the bottom, and this is the key thing, within fluid dynamics, there exists something called the particle relabeling symmetry. So at the top, we would discuss individual fluid particles, and they satisfy all the Lagrange equations. These are ODEs, but to then describe a fluid, you would have to solve uncountably many of these ODEs, and that's infeasible. But luckily, there's a symmetry, and the symmetry is really, really useful, and means that we can go into the Eulerian picture, where we discuss the evolution of vector fields and one forms rather than individual particles. And then we get the Euler-Poincare equations, which are the equations for fluid dynamics. And the mechanism that turns this reduced Lagrangian into equations, that is the Euler-Poincare principle. So this arrow at the bottom, pointing from the back left corner to the front left corner, that is the Euler-Poincare principle. So we'll focus fully on this left-hand side. We'll ignore the Hamiltonian side completely and just discuss this bottom arrow at first. But let's see how we get from a Lagrangian on particles to a Lagrangian on fields first. So suppose that we have such a Lagrangian. So usually for fluids, this would be the kinetic energy of a particle. And there could be potential energy coming from advected quantities. So for instance, in fluid dynamics, we would always have a density that's being advected, but you could also consider situations where you have magnetic fields or temperature or buoyancy or salinity or any of these sorts of advected quantities. You can also discuss active advected quantities, as Diego showed in the first talk, but those require a bit of more special treatment. So in this, when we talk about advected quantities, we always mean the passive ones. Okay, so now suppose that this Lagrangian is right invariant under the action of the subgroup that leaves the advected quantities at their stationary point. So that essentially means that the subgroup consists of these smooth maps with smooth inverses that leave the initial point of the advected quantity invariant. Then we can do some computations. Now, instead of working with the subgroup, we actually prefer to work with the entire group. And so we construct a Lagrangian that depends parametrically on these advected quantities. These A0s, they live in this V star. So then a general description looked as follows. So eta would be a diffeomorphism. So this would be the velocity of a particle. This would be the position of a particle. And this would be the state of the advected quantity. Then we write a new Lagrangian where we introduce this parametric dependence. And then we hit it from the right by eta inverse. Now, the benefit of that is that this little eta here then gets removed because it becomes the identity. The identity is unique. And then we define a new Lagrangian again, which is little l of A0 that just depends on this DDT, this vector field. And then we reinstate A0, but in order to do that, we have to push it forward. And that defines our Lagrangian on fields, because this particular equation here, that relates the particles to the vector fields. So here I have an equation. This is the reconstruction equation. It says that the particle initially at point X, that is the flow of that thing is defined by this eta, and eta depends on the vector field. So this equation is the key equation that allows us to first of all go from the top to the bottom. But when we have solved equations of fluid dynamics, also allows us to reconstruct the particle trajectory. So that's why this equation is important, and it's known as the reconstruction equation. And then for the trajectories of the advected quantities, we would simply differentiate A, and that means we differentiate the push forward of A0. That gives us this Lie derivative object that we saw before, so transport in other words. So if A is a scalar function, then this would be simply minus u dot grad. So this gives us the advection equation. So that's also where this advection equation comes from. Okay, moving on. Then we can talk about transfer principles, because now we wish to have this picture of the previous slide and have a stochastic version. So there's several transfer principles. The key one is Malyavand's transfer principle, and it says the following: geometric constructions involving manifold valued curves of sufficient smoothness can be extended to manifold valued processes by replacing classical calculus by Stratonovich calculus. Then there's also an Ito transfer principle. It's a bit lesser known, but it exists nonetheless. It requires less smoothness than its Stratonovich counterpart, but from the geometric point of view, it requires an additional structure on manifolds. And then there's another version, which is called the Schwarz transfer principle, which is a fairly recent development. And this is a second order version of Stratonovich calculus. So it's like Ito, but still Stratonovich in terms of it involves second order terms. That is also possible, and that's investigated in this paper by Huang and Zambrini. This is the one that we will focus on. We'll focus on Malyavand transfer principle. So that means I will replace this reconstruction equation by a Stratonovich differential equation. So that's what we'll do. So recall this deterministic reconstruction equation. It's simply a relation that relates the curve, the flow of a particle to the vector field that induces such a flow. And provided that this U and this psi I are smooth enough, then Malyavand's transfer principle gives us a stochastic reconstruction equation. So you recognize the original equation becomes the drift, and then to this gets added a Stratonovich term. So if we do this, then we can first have a look at what it would do to advected quantities. So suppose I have differential K forms, but for simplicity's sake, you can think of this as simply a function. Then you would have the stochastic Lie chain rule, which evaluates the following. So if you would take the differential of the pullback of such a differential form, then you get a SPDE, and this SPDE is the scalar transport PDE in the case for scalar functions. So here you see that you get this transport noise to come out. So you see in Daniel's talk, we saw that there was a transport operator transporting the fluid vector field, and it had a deterministic part and a drift, and that's it had a drift part and a diffusion part, and that's exactly what we see here. And then there's a convenient notation that you can introduce, which is this circle DST notation. That is more than convenient, because you can in fact use it to construct more general principles, where you replace this Stratonovich term by general semi-martingales. That's also possible, and it's something that Dan Creason and Oliver Street looked into. Suppose now that this K, if this is conserved along the flow, then the differential of the pullback is 0. And then this, in fact, then delivers the stochastic transport equation for this quantity K. So this would then really be the transport SPDE. And together with Aitami, So, and Darrell, we showed that this is an incredibly powerful formula in the context of fluid dynamics. And for instance, it also means that if I have vorticity in 3D, which is a two form, or you can think of it as a vector field. A vector field is not simply transported, it also can stretch. And so that means that you also need to include a stochastic stretching term, and that comes from this formula in particular. Okay, so then what is the stochastic Euler-Poincare theorem? Well, we now have all the ingredients to assemble it. So Hamilton's principle of least action holds for variations that vanish at the endpoints in time. So that is essentially saying that the first variation of this action vanishes, and that is equivalent to saying that the eta satisfies the Euler-Lagrange equations. Now, we know that those are annoying to write down in for fluid dynamics. So instead, we look at the reduced version, and it says that the constraint variational principle, so variations of this reduced Lagrangian that we saw before, this also vanishes, but we have to use specific variations because we have a certain symmetry at work. And inside these variations, you see the reconstruction equation at work. And then if you calculate what the Euler-Poincare equations are, you get what you see at the bottom. So this, of course, is in this geometric mechanics notation. So essentially what it's saying is that the rate of change of the momentum is transported. And on the right-hand side, you see all the forces. And these forces arise from the advected quantity. So for instance, if I have a compressible fluid, here I would have a pressure. This would be the continuity equation, and the relation between those two would be an equation of state. Okay, so if I apply this stochastic Euler-Poincare theorem to the Lagrangian that corresponds to the stochastic Euler equations, then I see that I have half mv squared, so the kinetic energy, and then I have a term that puts the whole thing into a rotating frame. So I have the rotation gets introduced into the Lagrangian using a term like this. I have to introduce an incompressibility constraint. So I want this U to be divergence free. And if I do that and apply this Euler-Poincare theorem from the previous slide, then I get these equations out. And so here you see the stochastic transport. You get two terms because this U is not a scalar function. It's also not a vector of scalar functions. It's a geometric object that transforms like a geometric object. And that means you get this additional stretching term. And then you see that there are two pressures because the vector fields that I want incompressible also have to make sure that the size, these additional things that I introduce are also divergence free. So I have a semi-martingale pressure, and in a deterministic case, you get a cancellation between this term and the gradient of the Lagrangian. So that would give you the Euler equations. Now, this means that this particular description is not too pretty to look at. So we prefer to go to the vorticity formulation. And in the vorticity formulation, it has the following, it looks like this. You get the transport of vorticity, which in 2D is a scalar function, by the Jacobian of the stream function with the vorticity. And then you also get this for the noise, where here we've used the incompressibility constraint. So incompressibility means that for the vector field U, there exists a potential, which in this case is the stream function that generates this U completely. And then the same thing would be true for these psi i's, and we call that potential sigma I. So these are scalar functions. So this is the SPDE that we're interested in, and this SPDE is coordinate free. So it looks the same on the sphere, except that, of course, everything has to be interpreted in terms of spherical coordinates then. So here you would have the spherical Laplacian, and the Jacobian would be the Jacobian corresponding to the sphere, which is a term that has this 1 over r sine phi term appearing that you wouldn't have in the in the flat case. Right. Now, stochastic Euler on the sphere has an infinite number of conserved quantities that are formulated always in terms of the vorticity. In particular, any integral of an analytic function of omega is conserved. And that means in particular that all LP norms of the vorticity are conserved. And now comes the key thing. So on the sphere, we have a numerical solver that preserves n of these monomial Casimir invariants. So these things are called Casimirs. When the resolution is n squared. So if we have n squared degrees of freedom, we're able to preserve these things up to power n, and that's also true in a stochastic case. So that's the big benefit that you get from this geometric construction, that these things are conserved. So if we zoom out a bit, in a geometric construction with transport noise, the energy becomes stochastic, but the geometry stays the same as before. Okay, so now we can try to simulate this a bit. And so now we get back to the promise. So to set up simulations, we followed remark 2.6 in Franco, Lucio, and Dejin's paper. But we simply changed the domain from the torus to the sphere. And then what we see is the following. So this is a simulation of the kinetic energy. And for deterministic Euler, the kinetic energy is exactly preserved. And for Navier-Stokes, it decays. And we see that if we introduce the type of noise that is proposed in this paper, we see that it does look like Euler goes towards Navier-Stokes. But as we increase the resolution, there seems to be still a barrier. There seems to be a gap between Navier-Stokes and these particular trajectories. And we think we have an explanation for this, and that is on the torus, there's no curvature because it's a flat space, and the convergence of the noise towards the dissipative term, that dissipation will be a Laplacian. But on the sphere, you have multiple choices for a Laplacian. So it depends on which Laplacian you want to converge to, I guess. And the Laplacian we've used to simulate here Navier-Stokes is a Laplacian that also includes a curvature term. And so it might very well be that the convergence holds in the flat case because there's no curvature. But on the sphere, it would converge to the spherical Laplacian that doesn't take into account the curvature. So that's a little conjecture that I'm willing to propose. Could be really interesting to see if the scaling limit is exactly the same on the torus as on the sphere, but ignoring all the curvature. So that is something that I wish that would be interesting to look into. So in general, so stochasticity can be introduced in geometric mechanics in several elegant ways. So with these elegant ways, I mean these different transfer principles. On the sphere, there seems to be some sense of convergence of stochastic Euler to Navier-Stokes. But then there's several open questions, because with this transport noise, we know that these Casimir invariants are conserved. So when we investigate the convergence of Euler to Navier-Stokes, one of the things that pops up is Navier-Stokes doesn't have any of these invariants because it decays all of them. It also decays the entropy and all of these Casimir invariants. But transport noise preserves precisely those Casimir invariants. So that's what I mean by the question, in what sense do the invariants of Euler converge to the non-invariants of Navier-Stokes? So is there something in the scaling limit that breaks down these geometric conservation laws? And so in particular, then, is there a key difference between energy, which is not conserved in the stochastic case, and Casimirs in this sense, which are conserved in this stochastic case? And then, as I mentioned, to which Navier-Stokes model are we converging? Because on manifolds, we have several choices for Laplacians. So it could be that it converges to the Bochner Laplacian, which is the Laplacian that doesn't take into account any curvature, or the Ricci Laplacian, which has this thing into account. So this is a cool open question that I think could be interesting to look into. Well, thank you very much for listening.
Thank you. Thank you very much. Are there questions?
Yeah, and here's some references.
Yeah, so we have Franco Flandoli, who want to, I guess, raise his hand.
Thank you, Erwin. Concerning your question about the convergence of invariants, the point is that the convergence is either in a distributional topology with respect to the variable used.
Yeah, in which we wouldn't have those invariants to start with.
Or in a weak sense against test function, but not in the basic topology of omega that you consider. So there is nothing to do with it.
Right, like that makes sense. Yeah, thanks.
Thanks.
And you also have a question in the chat by Andre.
Yeah, let me.
So how to derive scaling limits on the sphere? People involved in spherical random fields research frequently use Malevin-Stein calculus. Is it helpful also for stochastic fluids on the sphere?
That's a good question. I think it would be, because the Malevin calculus is really the pathwise approach that you would look into at this top level, where you would have these interacting particle systems. So I guess it's the case, but I don't know enough to give you a very confident answer about this. I think it would work in terms of a particle description of stochastic fluids, and then the field description can be done with the methods that Lucio, Franco, and Dejun looked into. But yeah, otherwise I wouldn't know.
Okay. So if there are no more questions, let's thank Erwin again. I will move to our last speaker, Milo Viviani.
Yes, I share the screen.
Yes, please.
Okay. So you should see full screen, right?
Yeah, perfect.
Okay, so I would like, of course, thank the organizers and for inviting me and giving me this opportunity. I just want to say that I don't come from the community of stochastic analysis, so I will try to tell something that I work with Francesco Grotto and Marco Mito recently, and I will not enter in detailed stochastic analysis, also because our work was not about that, but it was more like, in a way, a numerical approach to a problem which arises in the free dynamics and in the regularization of point vortex dynamics. So it's a problem which comes from, in a way, the more applied side of fluid dynamics and to the turbulence. And on the other hand, this problem also is a central problem in SPDEs. And we tried with this work to get some insights from a numerical approach in this problem of, as the title says, zero noise selection for point vortex dynamics after collapse. So let's start with the talk. Okay, so as you probably know, this is the 2D Euler equation. These are the 2D Euler equations in the vorticity formulation, and we will see we will talk about the dynamics of the vorticity field, which is the curl of the velocity on a flat space. So in our case, we take as a domain R2, and psi is the string function. So I will not spend much time on these equations that you all probably know. And so we have global exposedness in R2 for as a classical result for an initial vorticity which is bounded and in L1. Then related to the 2D Euler equations, since the 19th century, it was sort of found this set of finite dimensional it's a finite dimensional system, so it's a ODE, which sort of models the position of some of the center of mass of some vortices, and the motion of these vortices is an Hamiltonian system. In our case, then the space becomes R2n, and so we track the motion of the center of mass of our blobs, which are denoted with the xi, and the vorticity strength of each vortex is captured by the constant gamma j, which can be either positive or negative, depending on the rotation, the sign of the rotation of the vortices. So these equations have been studied extensively and are still studied actually in different communities, both from pure analysis, or then we will see also stochastic analysis, but also in the geometric mechanics. So this system encodes a lot of symmetries and a lot of interesting solutions. And it was presented and proved in the classical book of Marcœur and Pulvirenti that for almost any initial configuration, with respect to the Lebesgue measure, this system has a global solution. And however, there are configurations for n larger than 2, so for more than 2 vortices, which somehow exhibit a blow-up of the velocity field in finite time. And these solutions are called collisional configurations for the point vortex system. And actually, this set of collisional initial configurations has zero Lebesgue measure because of the result of Marcœur and Pulvirenti, but it's dense for n larger than 2 in R2n. What is the link between and why point vortex are interesting from a fluid dynamical point of view? Well, if we consider the empirical measure defined by the Dirac delta centered in the positions of the vortices xi, weighted with the vorticity strength gamma I, then this distribution actually solves the Euler equation in the distributional sense if the self-interaction of the vortices is neglected, and this can be seen via the Choquet symmetrization trick. And so point vortex equations also can be obtained as a limit of smooth solutions of the Euler equations. And there are several results showing that point vortex can model the center of mass of vortex patches if they are sufficiently far apart and for a certain time. But also the interest part of, from a geometrical point of view of the point vortex systems is that they represent a finite dimensional coadjoint orbit in the dual of the divergence free vector fields. And this is presented and studied, for example, in the work of Marsden and Weinstein in 1983. So point vortices arise as examples and non-trivial examples in very different areas of mathematics. And this, I think, is part of the fascination of studying these equations. But here we are interested in actually the collisional initial configurations. And in particular, since we want a selection principle to continuing the dynamics after the collision, we just can look, for example, at the deterministic regularization. And this was studied in 2016 by Godot and Sakhayev, where they regularized the Biot-Savart kernel K via some convolution kernel ρ. And then this convolution kernel is parametrized by some epsilon, which when epsilon goes to 0, then we have a continuation for our dynamics after the collapse. And in particular, if we have collision of point vortices, let's say in one point in the origin, let's consider, for example, the simplest case. So we consider 3 point vortices collapsing in the origin. So an infinite time etc. Then for epsilon going to 0, the regularized solution converges to the original solutions of the point vortex system, whereas after the collision time, the point vortex regularized converge to the same solution but symmetrized with respect to the x-axis. So there is a unique outcome from the deterministic regularization, which in a way, after the collapse, copy in a symmetrized way the original trajectories. Okay, but here we are actually interested in stochastic regularization. And here I refer to the work of Flandoli, Gubinelli, and Priola from 2011, where actually a transport, a multiplicative noise type is considered, but in that paper also is discussed a little bit briefly the additive noise regularization of the point vortices. Anyway, we consider our system of point vortices, so we consider the original point vortex equation, where it's added for each vortex a 2D independent density distributed Brownian motion, and we have pathwise unique strong solutions for each time in the sense of solution in the sense of SDEs. And in particular, so this SDE is well posed for every initial condition. So now the question is, if we give an initial configuration of point vortices, so I call x1 0 epsilon, x2 0 epsilon, x3 0 epsilon, which is collapsing when there is no noise. So we are interested in the limit for epsilon going to 0. So we know that for each epsilon we have actually a solution, even for this initial configuration. So what happens when epsilon goes to 0? So because of the regularity of the trajectories of the point vortices, we know that there is a convergence law of the stochastic process for each given by the SD for each epsilon to some law defined on in this case in R2 to the power 3. So the problem is that this convergence is of course up to subsequences, and we don't have a pathwise convergence after the time of collapse. So then the question is actually, what is the limit law for this system? And this is basically the question we try to investigate. So crucial of our analysis or our study was to consider the geometry of the point vortex system. In particular, point vortices are characterized by symmetries which provide some set of first integrals. On the plane R2, the most important integral is of course the energy, but also due to the symmetry of the Hamiltonian, we also have the barycenter and the moment of inertia. This set of integrals provide the integrability of the point vortex equation for n equal 3 vortices. So indeed, for 3 point vortices which collide, the collision must be self-similar. So the vortices move accordingly in a triangular shape, which actually is only rotated and reduced. So in a way, it's applied a rotation and a homotety at any instant of time. And actually, it's possible to characterize the configurations which which provide a collision of point vortices in finite time. So in particular, as you see in the bottom of the slide, the intensities of the vortices must satisfy the first equation, whereas the moment of inertia must be 0. So these conditions provide and characterize the configurations which cause collision in finite time. And actually, sort of a possible way to study this dynamics is to only look at one of the vortices, because, as I said before, the collision happens in a self-similar way, so we can always rescale and rotate our configuration of vortices and see what happens. In particular, we decided to set the third vortices in the unit vector 1, 0. And then, as you see from the conservation of the barycenter, so the second conserved quantity, it's possible to determine x2 from x3, which is now just 1, 0, and x1, which is our degree of freedom. So we define the new variable z, the transformed x1, and then the integrals are just a function of this quantity. So h will be a function of z, which is transformed x1, and I, the moment of inertia, will be a function of z. So now we were just considering all these aspects in the deterministic case, but let's go back to our stochastic differential equation, which is parametrized by epsilon, and let's see how sort of the dynamics of z behaves when epsilon goes to 0. So the first integrals of the deterministic dynamical system are not conserved in the stochastic model we have considered, because we have just added an additive noise, so we don't have conservation of energy and moment of inertia for epsilon larger than 0. However, it's known that in the limit, the moment of inertia must be conserved. And it's not clear, actually, whether the energy should be conserved. And crucial also, it's to understand what happens when epsilon goes to 0 is to consider the set, which is defined by the intersection of the energy and the inertial momentum level. And we will see now why. So just to clarify what I said, we see here some picture of the dynamics of these three vortices. On the left, we see so the black stars are the point vortices at an initial time, and then they start to move in a self-similar way in a spiral, which goes closer and closer to the origin where the collapse should happen. But now, since epsilon is very small but still positive, so 10 to the power at -10, we don't have collision, and then the vortices reopen in a certain way, but the shape of the triangle has remained the same actually here. And then, most interesting, what happens if we look at the dynamics of z? So z is the transformed x1 in a way that x3 is fixed to 1, 0. So actually, we have the following. So here in the picture, C indicates the collision configuration, and B, the burst configuration. So when the vortices come very close, they reopen in the self-similar way. So what happens to Z is actually that for the time in which the vortices are far apart from the collisional point, so when the vortices are far from the origin, the point x1 stays fixed, because the point z actually stays fixed, because I'm just rescaling and rotating the position, so I don't see any motion. But what you see here is that this purple line is what happens close to the collisional point. So here, what happens is that the energy level, which is the black line, is perfectly respected, or almost perfectly respected, by the dynamics of the vortex. So here now, what is actually happening? It's happening that the Brownian motions, or the Brownian motion that affects the z or x1, as or plays like a central role. So it's in a way larger than the Hamiltonian vector field. So the dynamics here is mainly ruled by the noise. But the noise acts in a way that the energy is essentially preserved. Whereas if you look at the angular momentum, it's much less preserved. So what you would see in the limit of epsilon going to 0 is just a jump from C to B, because in a way, the vortices will will directly jump from the collisional configuration to the burst configuration. And I wanted to remark also that the Hamiltonian and the angular momentum are actually local martingales. So we don't expect larger drifts of them. Okay, this is a possible outcome, but what we found numerically is that this is not the only possible case. So what can actually happen is that there are configurations due to some sort of choice of the intensities of the point vortices, in which the dynamics of Z still follows the energy level and can be really far apart from the inertial momentum level. And actually here we see that the shape of the triangle is respected after the collisional point. But we found also that it's possible another dynamics in which the shape of the triangle changes. And this is actually due to the fact that the intersection of the energy level and the momentum level can be either 2, 3, or 4. When they are 4, it can happen that after the collapse, this configuration, so the triangle are not any longer similar to each other. This is in stark contrast to what is observed in the deterministic case, in which the shape of the triangle is respected. And this behavior, so here we show for epsilon equal to 10 to the power minus 10, is very stable after even a smaller epsilon, even a larger epsilon, and it stabilizes. So it's not due to any numerical issue, and I will explain also why in a minute. So the numerical scheme you have considered is actually a very sort of ad hoc numerical integrator, because it involves symplectic integrators. So the deterministic equation of the point vortice is an Hamiltonian system on R2. So the best known way to integrate this kind of system is the so-called use of geometric integration, which involves the use of symplectic integrators. So these are discrete maps which preserve the symplectic form and solve modified Hamiltonian system. So these integrators exhibit nearly conservation of the Hamiltonian and exact conservation of the symplectic form. However, in our case, the symplectic integrator we used had to be adaptive, since the vortices become closer and closer. And in particular, we have used the midpoint scheme, and we have set the time step in a way that the scheme could get closer and closer to the collision. And you see in the bottom of the slide the way we have chosen the adaptivity of the scheme. So we had to define this function sigma, which is related to the Biot-Savart kernel, and get some power alpha to make the scheme work. Then for the stochastic part, we have considered a midpoint scheme which is adapted to Hamiltonian systems in a way that for quadratic and separable Hamiltonians with the additive noise, the scheme is able to capture linear drift of the Hamiltonian. And this was derived in 2014 by Barrage and Barrage. And you see that the scheme is the following that I wrote here below. So this is the method that we have used with the adaptivity of the time step, which is presented here below. Therefore, we checked how much the total energy and the angular momentum and the other barycenter are conserved by our scheme, and the conservation of properties of this numerical method are very good. So what we found, it's not affected by numerical errors. At least numerical errors are negligible for our observations. So then, looking at the trajectories we had in the previous slide, what we tried is to find statistics for the limit distribution, which was the question we asked at the very beginning. So what is when epsilon goes to 0, what is the limit law of the point vortex system. And actually, so the law we are looking for is something which should determine the reopening of the three vortices while after the collisional point. So it was believed, at least as a conjecture, that there could be a uniform distribution of reopening angle. In a way, there is no memory of, or that was the conjecture, that there was no memory of the initial configuration of the vortices. But actually what we found is that there seemed no uniform distribution of the reopening angle. And the angle, the reopening angle is defined as follows. So we consider, for example, the vortex x2, and we measure the angle with respect to the x-axis at double the time of collapse. So in a way, the same time that was spent of the vortex system before the collision. There are strong fluctuations of the CDF of the angle theta while we change the epsilon. So there is no also a stabilization of the law to a certain characteristic law, let's say a limiting law. So this means that the limit could be not unique. And we tried to evaluate the p-values to the hypothesis of uniform distribution for theta, and the p-values are very, very small. So this means that we have to reject our hypothesis. However, interestingly enough, and this is an observation that still we are not able to prove, we got actually very strong evidences also from the p-value that when we have for intersection of the energy and the momentum level, the chances to get either one reopening, so non-similar triangles, and the other reopening, so similar triangles, there is a uniform distribution on these two. So in a way, somehow, it seems that in this perspective, the system has no memory. So it could, the configuration of the point vortices could reopen in one of the two shapes without any considerations in how the configuration was at the beginning. And to conclude, I want to show the empirical CDFs that we derived. So the red line that you see is the uniform distribution, and the blue line is the empirical CDF, and the dotted lines are the confidence band for 95% of the empirical CDF. So we see that there is no evidence, actually there is evidence for not being uniform, the reopening angle. This is in the case when there are just two intersections between the energy level and the angular momentum level, and the same holds for the case when I have four intersections. And here you see it's even more evidence that our CDF is really, really far from the uniform distribution. And therefore, in conclusion, I want to say that we, in a way, found some sort of result that might indicate that it's very non-trivial to prove that, or to show that there exists a unique limit for the law of the point vortices while epsilon going to infinity. And actually, it might be that the limit is not unique. Further, it's not clear, actually, which is the limit law and how this especially is related to the initial configuration of the point vortices. More achievable seems to prove that actually the configuration, the reopening configuration of the triangle is uniformly distributed among the two possible configurations when these are present. That's all, and I thank you for your attention.
Thank you, Milo. You have a question, two questions in the chat. So the first question is by Erwin. What happens to the order of convergence of the stochastic numerical method when you introduce adaptivity?
Right. So for the stochastic part, that's actually a good question. I don't have an answer because I don't know if there is. I'm not aware of any result in this perspective actually. So I expected that the order of convergence should be the same without adaptiveness, because what we can do is actually to reformulate the same numerical method, modifying the Hamiltonian. So it's called the Darboux transformation. And the Darboux transformation actually puts the function sigma in front of the Hamiltonian in a way that that the singularity of the Hamiltonian is healed by sigma, and somehow in this way we don't have any more to adapt our time step because our time step now is fixed, and what changes is actually this coefficient in front of the Hamiltonian.
Right.
So this it's called actually Darboux-Sundman transformation, and it's equivalent for our numerical simulation. So I don't think the adaptivity in this case will affect the order of the numerical scheme.
Thanks.
You can look in the book of Eirer, Lubick, and Wanner about this Darboux-Sundman transformation. Yeah. So yeah.
The second question is by Lucio. Is there any interpretation of these results in the context of spontaneous stochasticity and 2D turbulence?
Spontaneous stochasticity, I don't know. I mean, in which sense? What would be the spontaneous stochasticity?
So Lucio, would you add something to your question?
Yeah, sorry. I mean, it's a very vague question indeed.
No.
So,
But...
I mean, so yeah, I mean, okay, with spontaneous stochasticity, I would say in general, the limit law, if it exists, is non-trivial, which, I mean, I guess here always seems to be the case. But somehow, I mean, the question is more related to the link with dissipation of energy somehow. So, I mean, yeah, there are some key differences sometimes between like non-uniqueness or stochasticity of the forward trajectories and inverse trajectories, for instance. And I don't know in this kind of dynamics if they play any relevant role.
Okay. Okay, so the fact that the continuum, so there is not really a selection principle or one trajectory, but there is sort of a limiting law, then yeah, in that perspective, yes, it seems that this.
But also the limiting law must be random, not deterministic. Also, that is important, which is your case, no?
Yes, yeah, exactly. Yeah, it's not concentrated on. It's not like a direct delta on one. Is that what you meant?
Exactly.
Okay. Yeah. It seems that it does not concentrate on any specific path, any specific trajectory. So the limiting law is. I mean, this, of course, it can be something that we observe, and epsilon should be even more smaller than the one we tested, but yeah, our results point in that direction, so that the limiting law is it's not uniform, but still is some let's say some Lebesgue absolute continuum law. And about turbulence is so the fact of adding additive noise to the point vortex system somehow should simulate Navier-Stokes to the point vortex. So yeah, then the fact that everything gets complicated is maybe a symptom of turbulence in a way. So that the zero noise limit is actually it's capturing some complicated phenomenon linked to turbulence. But I cannot say more than this.
No, yeah, it was. I mean, it's a very big and complicated topic. So thanks.
Welcome. You're welcome.
The way I wanted to comment more on the same topic, because also Lucio mentioned the difference between the forward and the backward characteristics, which is related more of the dissipation of passive scalars. But since this is already a vorticity of a fluid, one could also ask, without looking at the characteristics, one could ask, we have vortices. These vortices generate a velocity field with some energy, or rather say, the interaction between these vortices is given by an Hamiltonian. So you have an energy. You can ask how the energy changes before collapsing, let's say, and after the continuation.
Yeah. So
because you have a certain energy, then you collapse, and then you open again with a distribution of different shapes, with a probability distribution of these different shapes. How the energy of the different shapes changes when you...
No, the energy is the same. That's actually what these plots seem to indicate. So it seems that the black line is the energy level, and before the collapse, I mean, actually even during the collapse, so when the noise starts to play a role, then it seems that the energy maintains its level. So at least in this variable z, in which it's rescaled and rotated the triangle, the energy seems to be conserved before and after the collapse. And this also seems to indicate that it's not possible to have, or this zero noise limit does not select those solutions in which the three vortices remain joined in one point. So it seems that actually, since the energy in this variable looks very strong as a first integral, even in the zero noise limit, it seems that it's not possible to have in this selection principle to have solutions in which the vortices remain attached even for a while in the collisional point. So it seems that they have to reopen immediately. And how do they reopen? They reopen in a way that the energy and the momentum are conserved. Then, even conserving energy and momentum is not enough to say the shape of the triangle, because it can be either the one or the other. But they are forced to keep this invariant, at least in this. This is what the results indicate. That these invariants get all conserved after the collapse.
But also for say positive epsilon, the shape of the triangle changes more in some sense continuously, right?
What do you mean?
Okay, there's no notion of continuity, but what I mean is that if you look at the similarity class for positive epsilon,
yes,
you have something that is close to a certain triangle at for negative times, closer to another triangle for positive times, and you don't have like or when epsilon is positive, you don't have a sharp transition between these two similarity classes. You have more or less smooth transition, right?
Yes, right. Yes. So the triangle changes shape, and then it goes back either in the same shape or in another one in a smooth way. Yes.
And when it
this is actually what you observe here. So here is smooth. If epsilon was real 0, then you have just a jump from a configuration to another. Then what was the question?
No, I mean the question is that if you look at the similarity class, you have certain similarity class until the collapse, and afterwards you can change similarity class abruptly.
Yes.
But if epsilon is positive, and you can give a notion of topology, say on the similarity classes,
Mm-hmm.
you wouldn't see an abrupt change with positive epsilon, right?
Yes, yes, yes.
And so it is interesting to understand how the energy changes when you are close to this transition. But
Mm-hmm, mm-hmm.
I mean, I don't have a precise question, just
Yeah. To yeah, to me it seems that the energy is better preserved than the momentum. So I would also look at how the momentum changes in this in this transition. Yes, and yeah. Also, this also seems to be quite stable. It stabilizes for after a certain epsilon. So probably it's possible to have a better description of this kind of phenomenon more than like what happens to the CDF when epsilon goes to 0. This seems more seems a bit easier to describe, at least.
So I guess now we have a moment of free discussion, right?
Yes, maybe just before that, I would invite all the remaining participants to just unmute themselves for a few seconds and just basically thank all the speakers for the very great talks.
Yeah.
And now we can go with the discussion.
Yeah. So I guess if somebody has general comments concerning any of the talks, I mean, they're free to share these comments.
Yeah, actually, I have a comment. My feeling is that these are really high quality, deeply investigated talks, all 4 of them. So thank you very much.
Totally agreed.
So I have just a small comment, and it's for Daniel, because I mean, I really like, I mean, I liked all the talks, but I have thought about that problem at some point, so it's very interesting for me. So my question is the following. You have shown that with this type of boundary condition that you put for the Navier-Stokes, you can close basically the estimates for the commutators, which is the difficult part, somehow speaking, of Lie transport, of salt. You can close the estimates for L2, H1, but you can also go higher in derivative. So you can close the estimates not only in H1, but also in, I don't know, W27 or whatever. You can bootstrap somehow the commutator, or there is a threshold in the regularity somehow.
So, I mean, if we're ignoring the finite dimensional projections, so if we're just looking at the functions, then we can go to any WK2 in a product with the salt noise on a bounded domain. So long as the xi that we're considering, so we're looking at B of xi, so that needs to be 0 at the boundary, but it doesn't need any better boundary estimates. It just needs to be 0 trace. So as long as it's 0 trace and it's divergence free, then we can do any WK2 for that, for purely that term, not considering the Leo projector, not considering the finite dimensional projections. So the issue comes in with how we're getting rid of the finite dimensional, how we're getting rid of those projections. So for the Navier boundary conditions in this case, we can get rid of the PN at a level of W12, but then if we were to pass up to W22, then we wouldn't be able to get rid of this for general Navier boundary conditions, because now we have the same issue that And W22 is now the level that the Navier boundary conditions form a closed set, and this is not in the range of the Lie ray projector.
Okay.
But we do have something very interesting, is that because the Navier boundary conditions have this relation in terms of the curl, then we know what the curl of the Lie ray projector of something is. The Lie ray projector just goes away when we consider that curl. So if we then impose that the xi come to zero quite fast at the boundary, then we can take the curl of the P of the of our operator and then use this good, near compact support, going to zero fast at the boundary. So then we get that actually in the specific case of alpha equals 2 kappa, in that case where we required the curl to be zero at the boundary, then they actually do satisfy these estimates. So then we can go up to any level of WK2.
I understand.
But only then in the specific case that the vorticity is zero. If we didn't have that, we couldn't use this trick of hitting the curl on the Lie ray projector. So without the projectors, we're fine at any level. With the projectors, it really is quite precise. But with a very nice choice of boundary condition, we can still go smooth and smooth.
I understand. And of course, the problem is that the only way to, let's say, modify, you cannot use modifiers in bounded domains. Basically, that's the problem. So you have to use some kind of Galerkin approximation or whatever.
Yeah.
Okay. Thank you.
Daryl, you're muted.
Yes.
Thank you. Physically, is there any sense to have the boundary condition that the curl of the velocity is zero on the boundary? I mean, because a lot of people have thought about this, and it would really solve a lot of problems. But is there any physical reason for it?
So the boundary conditions in general, there is physical derivation. So as a hydrodynamic limit and in the theory of gases, there has been these boundary conditions have been shown to be viable, and in terms of modeling rough boundaries. But this is really only in the 2D case. So in the 3D case, we can impose that the vorticity is zero, and this doesn't quite overconstrain the problem, but then you're really stretching at what is physically reasonable. But in the 2D case, the general Navier boundary conditions are reasonable. For the vorticity to be zero, you're choosing something very specific. So you'd question how realistic it is to choose specifically alpha equals 2 kappa. But generally, there is physical backing for this. But in 3D, you're looking at a different story.
What's the physical backing? Really, oceanographers struggle with this a lot. If only this were true, then they could do things.
Let me find my slide where I say it, because I'm not one for the knowledge myself. So in the kinetic theory of gases and as a hydrodynamic limit, it's been shown to have uses, and for modeling rough boundaries. So if you have a smooth boundary with the Navier boundary conditions, and it has some modeling purposes for a rough boundary. But I really can't speak too much in terms of the physical relevance. I see someone says it might be useful when it solves my problem. So, hey, that's good. I'm going to use that.
Yeah. Okay. Thank you, Daniel.
Cheers.
But Daniel, also in prolonging the discussion, did you look at sort of general boundary conditions as well? Suppose you have a mixture of Dirichlet and Neumann that sort of balances exactly to kill the estimates. Is that the reason? Does that notion give rise to these Navier boundary conditions, or is it again even more special than that?
So I haven't actually looked at mixing the boundary conditions, what we could get from that. But on the geometrical perspective, so actually Oliver Street and Rio, I spoke with them about the geometrical significance of these boundary conditions, and they suggest that the Navier boundary conditions are more reasonable than the no-slip conditions from a geometric perspective. It's if they came from some other angle and seemed like they coalesced. I can't really speak too much on that, but I mean, particularly Daryl, obviously, very close touch with Ollie and Rio. So that's definitely something I want to pursue, to see, exactly what kind of geometric backing we can get for this. But supposedly, from their point of view, there is something there.
Yeah, makes sense. Thanks.
have a comment for Diego. I guess second to last of your slides, you had something about a sort of noise which was linear, but the modulus of the noise was proportional to the derivative of the solution, and also the Hilbert transform of the derivatives was, I mean, I don't remember precisely, but I was just, I just wanted to say that this reminds me of a result that I've seen by Bagnara and Maurelli, where they regularize Euler in this way. So they put like, I may be wrong, but I guess it is like this. So they put a linear noise, Ito noise, and the modulus of the noise depends on the higher Sobolev norms, and this regularizes. But I mean, I don't know if you are aware of this paper.
No, actually, what is Morelli and who else?
Bagnara.
Okay, I'm not aware. I'm not aware, to be honest.
I may be wrong, but
okay. I will take a look at it. To be honest, I did not know about that paper. So, but the paper takes about SPDEs, and they.
Yeah, Maurelli is here. So Mario, please.
Okay, sorry.
No, thanks. No, actually, our paper came after yours, and I think it's very much in the spirit of yours, but it's for Euler equations. So we are the kind of superlinear noise in the spirit of you have, and proved by the mean of Lyapunov function that can avoid exclusion. It's also similar to a paper. There is also a paper by Tang and Wang. Our paper, just to say, it's me, Bagnara, and Su. Okay.
Yeah, sorry.
Yes. Thanks.
Yes. So I know that the idea of putting this, let's say, strong linear noise, which is this nonlinear stuff, it's not new. This I completely know. Actually, I think it was also used for some kind of beam equation, I would say, even in 2005. Yes, exactly. And yes, this I know, but the idea for me was basically that since in the deterministic case, this result proves that you have always singularities, I just wanted to check if even for this one-dimensional, which is non-local and non-linear, and it's somehow a little bit special, if you could put let's say, strong noises that avoid the typical singularities, which was something that we thought it would work, but we wanted also include it that it could depend on time and, let's say, make it as general as possible. But it was basically also for completeness, because we showed something like some noise that provides you singularities, the other ones that prevent singularities, and, let's say, general noises where you can put where you can show local well-posedness and uniqueness and typical stuff. Yes. One important thing is whether this idea could be done. I mean, it would be very nice to, for instance, show whether you can do this with transport noise. Of course, I mean, this is I would say the dream somehow. But even some question that I thought about some point is. So we showed with Aitami Betancourt and Takao that for the Borges equation with transport noise, for some particular cases of the noise, you cannot prevent shock singularities. So shock singularities also occur. And something interesting is whether you can also show that you cannot prevent the singularities in the CCF model when you put transport noise, not a multiplicative noise, but transport noise. This would be something I think it's interesting. I don't know how to do it, but it could be interesting.
If I am allowed to reply, I'm sure it's okay.
Sure.
Yes, no, you're totally right. I mean, it's somehow yes. So it would be nice to do it for transport noise. I was just wondering whether, I mean, when you say you expect maybe not to have to avoid shocks, do you mean linear transport noise?
Linear transport noise.
And because maybe the idea one may try to take a non-linear transport. What I mean is something like grad theta. I don't remember if it was theta or not, but let's say theta equals the variable, and then the stochastic velocity field is not given, but is rather depending on theta itself in some ways. Might be kind of reasonable. I have no idea. So this I don't know. This would be I mean, to me, it would be a nice things to do.
This I don't know either, to be honest. This I don't know either. I mean,
if I can also,
even for the even for the linear transport noise in 1D for Burger's equation, we could not even prove that any kind of Xx prevents the shock. We had to choose a very particular combination in order to prevent the shock. So there are even, for the linear transport noise, there are even cases which we could not really show whether it prevents shocks or not. So even probably with non-linear stuff, it could be nice if we can prove that non-linear transport noise can show, for instance, global well-posedness for Burgers. I mean, this would be very nice. But I don't know how to do it.
I mean,
if I can very shortly add, on my side, another related question which could also be very interesting is not whether the noise prevents the blow up, but whether the equation with noise still has a unique weak solution as a continuation after blow up. Like not really preventing, but rather sort of restoring well-posedness in a class of actually weak solutions which still exist afterwards.
This is very interesting. I don't know, for instance, are there any kind of results in that directions for non-linear equations and non-local equations? I mean, not for continuity equations or things like this, which I know they exist, but for things that are more involved, are there any kind of results? I don't know. I mean,
so of unique continuation after blow up. So yes. Where really blow up also happens. I think maybe there was a paper by Franco with Delarue on Blazo-Poisson.
Exactly. Yes, it's very particular because the solutions are pointwise solutions, so the sum of delta Dirac. So it's extremely particular class of solutions, but the result is precisely a unique continuation after blow-up.
Does Benjamin guess of something in this direction for hyperbolic conservation laws, perhaps? That might be another similar direction where you could find some related results, but I'm not sure.
I don't know.
But
yeah, Andre, please.
Do you hear me?
Yes.
Do you hear me? Yes, okay, thanks. It was extremely interesting to listen and too short time to discuss, but just two questions. Firstly, where are the areas in terms of probability, possibly also applied things, to apply these approaches? Naturally, those are related to stochastic fluids, but probably this could be applied also elsewhere. And also, how much you mentioned, say, Milo mentioned symplectic operators, so to which, and others as well, different things, to which extent do the approaches, general stochastic differential approaches, change using transport noise? Do you need any different, say, how to use rough methods, how to use regularization by noise that we already had a webinar? Yeah, I hope the question was covered. Voice. maybe applications or.
For applications, at least in my case, I have no idea about it, so I don't want to lie. I mean, probably, I don't know, Edwin knows a little bit more about numerics and so on, maybe can say something, but from my side, I cannot give any kind of information to that question.
I mean, application areas of this type of theory is sort of, I mean, it's not limited to fluids, it goes to all of continuum mechanics via the same sort of principles. You can also have the finite dimensional setting that Milo touched upon, where you really look at the Hamiltonian systems of finite dimensions, where you introduce these sorts of things, and then you can really talk about symplecticity and other interesting geometric relationships. So, I mean, I would say it's quite broad. And then the analytical results, like restoring of uniqueness for differential equations, where the vector field is only bounded measurable, and these sorts of results, then in the finite dimensional case, really directly connect to the usual setting. In the infinite dimensional case, much of this is completely open, as far as I know, at least. For the analytical story, then of course the others are more the experts. But I would say in terms of application area, it's quite broad. You can have many of these physical theories, anything that can be modeled with a Hamiltonian system, these results are immediately very interesting for. So that's, and then potentially also really cool for statistical physics. And we've seen some Hamiltonian Monte Carlo type approaches that benefit from irreversibility. And noise can be the mechanism that introduces this irreversibility, which means that you search through the space quicker and you don't come back to points that you've already visited, and these sorts of things. So in terms of application, I would say it's really broad. I am not sure if that was exactly the question, but
Thanks. It was. Thanks.
So Daniel and I were at a paper and at a discussion yesterday where Hao Tang was saying that these ideas are being applied also in parabolic equations and gradient flows. And for example, an interesting flow called the Keller-Siegel problem, which has blow up, and so they're working on what's the effect of the noise on that blow up.
Yeah, and then also it might add to this that there's also an interesting interconnection between chaos and stochasticity, because many people think of chaotic behavior as stochastic, but you can show in many cases that at least transport noise leaves the type of chaotic evolution completely untouched. They're sort of completely separate notions. And so that's another interesting thing. So you can think of stochasticity as a model for many things, but the type of noise really matters in terms of the modeling. So for instance, with this Lorentz attractor comes from Rayleigh-Benard convection. And so if you introduce into Rayleigh-Benard convection this type of transport noise, then you see the same statistical effect of chaos as you saw in the deterministic case, for instance, which is I think also quite a surprising result. That transport noise leaves these the chaotic nature of the system sort of invariant.
The field which is quite disjoint from ours is mean field games, where people use a lot the concept of environmental noise, namely they have particles. Okay, it can be also non-mean field games, but particles, interacting particles. But mean field games is more famous nowadays. And these interacting particles, instead of being subject to independent noises, each one, they are subject to a common noise. So they call common noise environmental noise. And when you take the mean field limit, in the mean field the mean field equation is stochastic with a transport type noise, usually in divergence form, like a continuity equation, but it's a transport type noise.
May I ask a question to Erwin?
Yeah, sure.
Yeah. So you said that on manifolds you don't know which Laplacian you should look at, or it's not like unique. But why this not apply for the flat case? Like why?
Yeah. So in the flat case, all of the choices for Laplacian are all just divergence gradient and and finished. At least for the scalar Laplacian, you have grad div, or sorry, div grad, and you're done. But div grad is also a Laplacian on manifolds, and it's a perfectly fine notion. But you also have d delta plus delta d as a Laplacian, and it's not the same one as the divergence of the gradient, because the other one has curvature in it. And so this is.
But you could have a non-Euclidean metric also on a flat space. I mean, it's,
no, of course, yeah, of course. So you can, depending on what you choose, there's different Laplacians, and if your metric has curvature, then you get a Laplacian that takes this into account and a Laplacian that leaves this out. And so then it becomes the question: what is the natural choice when you model Navier-Stokes? Because Navier-Stokes doesn't follow from a geometric principle. It's the Laplacian arises to model the effect of colliding particles and viscous friction. So that itself is a model. So there's not a direct principle behind this other than you go all the way down to the Boltzmann equation, you look at the collision operator, and then you find some sort of averaging limit towards this Laplacian term. But when you ask the same question on a flat space with a metric, for instance, that's non-trivial, then the question becomes, okay, what is this Boltzmann operator even, and how would you take such a limit? So the question is really, okay, the principle behind deriving the viscous term is really different on a curved domain. So I wouldn't know exactly what is Navier-Stokes on a curved space. I don't know. There's not a unique choice, it seems, because you have multiple choices for this viscous friction term.
Okay.
So Euler, of course, follows directly from the theory, because that's that is just the shortest path given the L2 metric on a domain. But Navier-Stokes arises in a different setting, because it's not a closed model. It also leaks energy because you haven't you've modeled away the collisions, and it turns into heat, but then the heat is not introduced in the model, so kinetic energy doesn't get converted into thermal energy, because thermal energy is not part of the model, and this sort of thing. So that the physical interpretation of that would then really be different.
No, just because at least if you have like domains embedded in an ambient space, then the induced metric seems the natural one.
Yeah, but then still the question is, if you would consider such a situation, what would be the choice for the Navier-Stokes viscous term? Because you can still choose in this situation. And this I don't know. I'm not sure if there's a good answer to which one is the more physically natural choice.
Okay. Thank you.
Andrei, I would like to sort of continue on this. So I don't know, is your raising hand related or an independent question? Just to know if you let you go first or.
Do you hear me? Do you hear me?
Yes.
You hear me
now we do. Yeah.
Yes. Thanks. So it's the question that we discussed just ahead of the webinar with Erwin. Do you hear me?
Yeah.
Do you hear me?
Yes.
Yeah. So the question is, how can this be related to interacting particle systems and in general stochastic processes like Levy or Brownian motions of any possible type? How could this be integrated within this? I'm more thinking about interacting particle systems because it's more complex in terms of particle dynamics, and all of this seems really related that you discussed same things on the sphere or other things that you described?
Yeah, so this is an interesting question because, well, the Navier-Stokes model itself, at least also in the geometric picture, we had on the top level, we have the particle description, so which is really then fluid particles, which are infinitesimally small and they cover the whole domain. If you would take a more physical theory, then you would have molecules of certain size that move around and interact with other particles, and that's the Boltzmann description. But then you would have this Boltzmann description of finite size particles on a curved space, and then you could ask, okay, what is the hydrodynamic limit of such a description? And I really have no idea if anyone has looked at this for curved domains. I know that the question is already quite challenging in flat space anyways, particularly with nonlinear interactions and complicated collision operators. So it's quite a challenging question nonetheless. On manifolds, I mean, the methodology would be very similar, but the additional difficulty is that curvature plays a role. And sometimes curvature really helps you. So in a lot of things on the sphere are particularly nice in terms of the analysis, because no matter what trajectory you take, they come closer together again. But if you would take the figure 8, which is negatively curved, then everything tries to move apart, and you get the exact opposite version. And this is also why the torus is nice, which sits in between the sphere and the figure 8, which is flat, because there you have exact control over how these things move. So yeah, it's a really, I think that the curvature for this, in terms of the analysis and particularly interacting particle systems, that would really affect the types of results you can expect, I think.
Maybe, do you hear me? Do you hear me?
Yeah.
Do you hear me? No. Do you hear me? Yes. Sorry if I repeat this all the time. So there are people, Lucio might know also, one in the YoungStatS, Alessia Caponera, who work with spherical random fields, perhaps connections of this research to other areas in probability and so similar stuff, I would say, would make a lot of sense as well. This would be interesting. You mentioned the sphere and stochastic geometry and other areas, I'm sure, related to what you described just.
Yeah, at least to the extent that I heard the last bit of the comment. Yeah, no, for sure. The spherical random fields and related areas of research could definitely be interesting for trying to settle or at least discover more about what happens to interacting particles with a stochastic process on domains that have curvature.
Okay, thanks.
Erwin, if I can make another comment about all this problem of identifying the right Laplacian. It could be completely off track, but just because when I was in the presentation, it was coming to my mind. So in the case of the torus, for 2D Euler to Navier-Stokes, there is actually somehow sort of another scaling limit that was observed by Franco and De Jun, which is in the case actually when you take the initial data sampled as the entropy measure. So you have this somehow this measure of distributions which is invariant under Euler. And in that case, if you try to perform the same scaling limit, you will not converge to deterministic Navier-Stokes, but you will have to converge basically to a stochastic Navier-Stokes with the right additive noise that basically enforces still preservation of the entropy measure. So somehow, since this preservation of this measure is preserved through the whole process, it also has to basically come through after the limit.
Yeah.
And so this could be somehow maybe suggesting what should be the right candidates of Laplacians. So, I mean, okay, in the case of the manifold, I guess, I don't know if the equation with additive noise makes sense anymore because you don't have an additive structure, I guess, or not necessarily. But again, it could be reasonable, like in the case of the sphere, there is the entropy measure for Euler on the sphere. I mean, as formal invariant. So it might suggest what is the right kind of Laplacian, and this is also connected to the problem of the connection you put on the manifold, I guess, because that gives rise to the L2 product, which sort of defines your white noise, and so the concept of entropy measure you're using. And then
exactly.
you just need to tune them to still enforce the same invariant measure. So could be a way to.
Yeah, that sounds perfectly reasonable. Yeah, it would I think it really does depend on the approach that you take. That the type of Navier-Stokes equation that you end up with depends on how you what sort of scaling limit you take. And then the beauty would be that independent of which scaling limit you take, you get the same equation. That would then really hint at which is the correct formulation, I think. Yeah, so I would second your idea for sure.
So about the transport discussion with noise, can I make some remark about it?
Sure.
Yeah.
So in turbulence theory in the 90s, Bob Craignon introduced this model of turbulence in which the advected quantities, just as a transport problem, were stochastic. And this led to a tremendous amount of mathematics. And he was approached by Gawecki, for example, using field theory. And it's one of the things that I was thinking of when I was thinking about the stochastic transport in the full system, not just in the advected quantities. But I think maybe it'd be a good idea to to look again at Craignon's model, because in the meantime there will have been 30 years of people looking at it, and there may be something that will fit together with this type of stochastic analysis that's now being done. And basically the noise was Stratonovich, but it depended on the wave number of the basically the wave number of the path.
So if I interpret that, so the noise was non-local then, or it was non-linear because it depended on the wave number?
No, it was non-local in the sense that he wanted this noise to produce a particular type of k to the minus 5/3 spectrum also. Okay, and a lot of people study this. Really, really good people were studying. And in the 90s, I was working in turbulence, and every turbulence meeting, there was a big component of Craignon's model. It was the latest thing on it. And so I think that maybe now with the advent of much deeper stochastic analysis, looking back at this model will be maybe a reward that could then spin off into a lot of work that physicists do, physics of fluids, and something that Erwin said is actually Greg Eink has been talking about how there is not a dissipation region, and that when you get into the molecular processes, it's just like you said, Erwin. He said that now you have to bring in thermal properties. Okay, and so that is actually a thing in physics with turbulence. And the Eink is spelled EYINK. Okay, and Yeah, I think it'd be kind of interesting to just look to see what are the physicists doing lately. You know, what are the physicists doing tonight? You know, and that I think it would be inspiring to, in the other direction too, to think in terms of completing the theory, to to find and discuss what's consistent with having proposed Stochastic's stochastic advection of the passively advective quantities, and what implications does that have for the motion equation for the fluids?
Yeah, for sure. But the link with Craignan is always a very inspiring one, because Craignan did some fantastic work, particularly for 2D turbulence, the -5/3 scaling that you mentioned, and then a -3 to go for the entropy cascade. And for us, this is one of the cornerstones to at least test the stochastic theories in. So that's also, again, why we insist on this sphere, because for the sphere, we have been able to establish exactly the -5/3 and the -3 numerically. So now we have a testing ground in which we can allow for these stochastic perturbations and see what happens. And with transport noise, we've now started the sort of the first simulations. We haven't really looked that much into the energy spectrum yet, but it could be because, I mean, for Euler, it has a sort of really weird looking -1 energy spectrum. And then Navier-Stokes has this -3, -5/3. And we saw that in this sort of preliminary simulations, if you add transport noise in the version of Lucio, Franco, and Dejean to the model, that you do see that it wants to, or it tends towards the energy profile of Navier-Stokes. But we haven't looked at how the energy gets distributed across the wave numbers yet. So that I don't know. That could be a very revealing argument on top, whether it has the correct sort of energy distribution rates that you would attribute to Navier-Stokes. Yeah,
energy transport rates. Yeah. There's a chance that the turbulence, the fluid turbulence people will get all excited about this if they can just hear about it a little more. Because they're pretty stuck right now. They're going to higher and higher Reynolds number. They call the local Reynolds number based on the kinetic energy of the fluctuations, called R lambda, and they're stuck because their computers can't go any better. Okay, and now they actually need some more models.
Yeah. Andre.
Do you hear me? Just checking. Do you hear me? Yes. How extendable is this further? I mean, is there something really so specific about the transport noise for stochastic fluid equations? Can it be replaced by other type of noise, or could progress go into development of transport noise, say, based on optimal transport and other related areas?
I guess it depends a bit on with the constraints that you put on to yourself. So if we are restrained by what you're allowed to do geometrically, then these transfer principles give you some choices. And so there are different noise theories from that point of view. But if you're not limited to the geometric notions and you also allow yourself just the noise terms to be forcing, then of course you blow everything wide open, and then you can use multiplicative noise, you can use additive noise, jump processes if you wish, etc. So it really depends on what you define as your physical restrictions, or at least not even physical, mathematical or physical restrictions, because we view the geometric notions. They give us the right physical laws, so we restrict ourselves to only allowing for noise models that comply with those laws. And then that restricts us heavily to only considering very specific types of noise. But you can certainly open it up and then say, okay, I'm not going to allow, or at least I'm going to interpret this as external forcing. So then it's not a closed physical model, then the noise comes from the outside. Like, for instance, this background environment noise that Franco spoke of with the mean field games analogy. So yeah, it really depends on what the source of the noise would be, I would say, in terms of what you allow for types.
Would this be extended also outside of sphere to any manifold, or even to complex manifolds?
There's no issue on complex manifolds. You do get because complex geometry gives you much more restrictive differential operators and etc. Because differential geometry on complex manifolds is a completely different animal to the real one. But that's the geometric part. How do you define temporal processes on those? That's where the noise usually enters from our picture. So we essentially have the same geometry as in the usual case, but the temporal processes are parametrized in a stochastic manner. So if you take that copy, you can print it onto complex manifolds as well without too many restrictions. Yeah. But then, of course, what it means for transport and so on, that's a completely different animal in complex geometry.
Thanks.
So I think if there are no further questions or things, I think it's a right point where to stop with the webinar. So again, thanks to all the speakers, and thanks Diego, Erwin, Daniel, and Milo. Thanks to Umberto for moderating the event. I think it was there were really nice talks. It was a great discussion afterwards, and thanks to all the participants for coming.
Thank you for organizing. It was really, really fun to participate, and thanks for letting us speak.
Yeah. Yes. Thank you very much to all the organizers and the participants.
Thank you. Thank you very much.
Thank you.
Thanks, everyone.
Bye-bye.
Thanks to all. Thanks to all. All right.
See you.